Hi everyone, this is Sharif Sami. The main topic of this video is about numerical methods for ordinary differential equation. Okay, now pause the video and read carefully question 1 before we proceed.
Open your mind. Open your mind. Not literally.
So, in the first step, we start with x1 and y1, which are given in the problem. From x1 we get x2 by adding the step size h, and from y1 we get y2 by using Euler's method. That is y2 equals y1 plus the step size times the derivative evaluated at x1 and y1. And accordingly we get the value of y2. So graphically we start with an initial pair of coordinates x1 and y1, and we get a new pair per step x2, y2. Now likewise in step 2 we start with x2 and y2 and we get x3, y3 as explained in the graph. This is the final answer of the problem, and we need around 8 steps to reach x of 4. And this is the graph for the function values evaluated using Euler's method. Now, the analytical solution, all we have to do is to integrate the derivative with respect to dx, and accordingly we get this term. And we have a constant c, which we will get through the initial conditions provided in the problem. We have at x equals 0, y equal 1. So by substituting back in the equation, we conclude that c equals 1. Therefore, this is the expression, or this is the analytical expression for our problem. So for the requirement of the problem, we need to compare the true and the approximate values of the integral. And for this, we will substitute with the values of x we have into the analytical and compare it with the ones we get from the Euler's method. And in addition, we will calculate the percentage true error. We can notice from the graph that having a step size of 0.5 resulted in a poor accuracy. And therefore, we have another question: how can we reduce the error? And simply we have to reduce the step size h. Now if we use a step size of 0.05, this is how close the values we obtained from Euler would be with respect to the analytical values. Now for the question 3, pause the video and read the question.
Open your mind. Open your mind. Not literally.
In the first step, we start with x1 and y1, which are given in the problem. From x1 we get x2 by adding the step size h, and we get y2 from y1 using Euler's method, and by doing this we get y2 of 5. Now this looks exactly like Euler, but we will call y2 here as the y predicted from Euler's method. So y2 from Heun's method is simply equals to y1 plus the step size times the average of the derivative evaluated at x1 and y1 and evaluated at x2, y2. And by doing this, we get the value of y2 as shown in the screen. On step 2, we do the same. We have x2, y2, x3 we get it by adding the step size, y3 we get it from Euler, and we will call it the predicted value of y3, and the y3 from Heun's method is the same, it equals to y2 plus h times the average between the derivative evaluated at x2, y2 and x3, y3. And by doing this, we obtain the value of y3. This is the solution of the problem. We will need 4 steps to reach x of 4 using a step size of 1. Now for question 5, again pause the video and read the question carefully.
Open your mind. Open your mind. Not literally.
So we start again with those initial pair of coordinates x1 and y1. x2 is the same, we get it by adding a step size to x1. We need to calculate 4 coefficients, k1, k2, k3 and k4. Now for k1, it's k1 equals to the derivative evaluated at x1 and y1. And by doing this, we get a value of 8.5. k2 is the derivative evaluated at x1 plus half h, and y1 plus half k1h. So when we encounter x and y terms in the derivative, we substitute with these values. So this translates into minus 2, and we open a bracket, x1 plus half h cubed plus 12 x1 plus half h squared minus 20 x1 plus half h plus 8.5. We don't have y terms here, but if we do, we substitute with y1 plus half k1h for y terms. And by doing this, we get a value 4.21875. Now k3, it's the derivative evaluated at x1 plus half h and y1 plus half k2h. This is the difference between coefficient k2 and k3, that the y terms are different. But in our problem, we don't have y terms in the derivative, so we will get the same answer as in k2. Now for k4, it's the derivative evaluated at x1 plus h and y1 plus k3h, and by doing this calculation we get a value of 1.25. Now after we get all these four coefficients, we can get y2 as y2 equals y1 plus h. We have k1 plus 2k2 plus 2k3 plus k4 divided by 6, and by doing this we get the value of 3.219. And in step 2, we do the same. We start with x2, y2. We get x3 same manner as before. Now we calculate k1, and we get k2, k3, and k4. And then we calculate y3 from the same relation. And in this case, y3 equals 3. Now, this is the solution of the problem. We required 8 steps. This is the same problem as question 1 that we used Euler's method to solve. This is the analytical solution of the problem that we obtained in problem number 1. This is the Euler's method. And this is using the fourth order Runge Kutta. Now you can notice here that the fourth order Runge Kutta is very close to the analytical solution and more accurate than Euler's method of the same step size of h equal half. Alright, this is question 7. Pause the video and read the question carefully.
Open your mind. Open your mind. Not literally.
Alright, we start here with x1, y1, and z1. We have here a system of ordinary differential equations, but there is nothing to worry about here. Again, x2 obtained by adding step size to x1. In Euler's method, it's the same rule, apart if we found z terms in the derivative, we substitute with z1. And in this case, y2 equals 3. Same thing applies for calculating z2, and by doing this, we get a value of 6.9. Likewise, in step 2, you can see everything here is systematic. So nothing new here, it just we do an extra calculation per step. This is the final answer of the problem. We will need 4 steps to get to the final solution. Right, this concludes our tutorial, and until next time, goodbye.